Good day, ladies and gentlemen. My name is Mahesh, and I'm in the R&D group of Yaskawa, America, here in Waukegan, Illinois. The topic of our presentation today is study of active filter techniques for reduction of harmonics caused by variable frequency drives. I have organized the presentation in the following manner. At first, I'll introduce the topic on harmonics, and I'll go over its significance in energy conservation in electrical power systems, and I'll discuss why variable frequency drives generate harmonics. Variable frequency drives are the workhorse of the industry, why they generate harmonics and why we should be concerned about it. I'll discuss some popular and new active harmonic mitigation techniques and its relevance in reducing the power system stresses and improving the efficiency in the power system. And I'll conclude my talk. This is a typical input voltage waveform which most people are aware of. It could be either a 60 Hz signal or a 50 Hz signal. This is what a variable frequency drive will be subject to, an incoming voltage. But the current drawn by a typical variable frequency drive is like this. It has got multiple zero crossings in the system, and it is not smooth as the input voltage waveform is. It has got multiple peaks. As you can see here, there's only one peak in a given cycle or a given half cycle, whereas here there are multiple peaks and multiple zero crossings. And in general, we can say that this waveform does not follow the voltage waveform. And such systems wherein the current does not follow the voltage, we call such systems to have a nonlinear relationship. The current has a nonlinear relationship with the voltage, and so these systems are called nonlinear systems. And what is the issue with the nonlinear system? The typical problem with nonlinear systems is that it creates losses in the power system. The RMS value of the actual current flowing here is much higher than the actual value of the current which is needed for creating a particular job, for moving a particular shaft at a particular speed. We need much more higher RMS current to provide the actual workforce. And basically that kind of a current waveform creates heating in the system. It makes the transformers run hot, the cables run hot, and so there's power loss associated with it. How do we find out how much loss is happening in the system? Is basically by resolving this. One thing which we have to understand is that heat which is produced in the system has a thermal time constant. It cannot turn on and turn off immediately. So for us to estimate heating caused by this kind of a current waveform, we have to resolve this current waveform into sinusoidal or continuous wave structure, which when combined together will recreate this kind of a current shape. And the effect of the higher harmonic content in the system is then evaluated as, okay, how much heat it causes. Especially higher frequency components cause transformer core losses, increases transformer core losses, and also skin effect in conductors carrying power or electricity. So resolving the nonlinear waveform into sinusoidal components is called harmonic analysis. And the ratio of the non-effective component in the current with respect to the fundamental component is called total harmonic distortion. That's how we quantify the effect of this kind of a waveform on a power system. So there are two important points or two motivating factors here. The first motivating factor, as I just mentioned, is basically the losses in the system. The higher distorted current waveform creates more losses in the system. We have to be aware of it to handle losses. The other thing is that the actual size of the system, the actual conductor size or the cable size or the transformer size has to be increased to handle this kind of higher RMS currents. So in other words, the reactive bars or the useless current which we have to carry to recreate this kind of waveform is a stress, is a burden on the power system. And so which we call it as system rich in harmonics is generally associated with poor power factor and low efficiency. Poor power factor means the VARs or the reactive VARs in the system is much higher than what we actually need. And that's why those are the two main motivating factors why we have to deal with non-linearities in a given power system. Why do variable frequency drives, which is the workhorse of the industry, why do they create distortions, or why are they responsible for creating distorted current waveform? That is easily explained if one looks at the front end of a typical variable frequency drive. The front end of a standard variable frequency drive has a 3-phase AC to DC rectifier. It's got 6 diodes there and a bulk capacitor. The capacitor is charged up through the diodes, and as most of us know, that this current will stop flowing once the capacitor reaches the line-to-line peak value of the line-to-line voltage. Only when the capacitor discharges will there be a current flow through the diodes to recharge the capacitor back. But again, when the capacitor discharges, we have to wait for the appropriate part of the cycle for the instantaneous voltage to be higher than the stored voltage across the capacitor for the current to flow. And that is why the current flows in pulses. It's a pulsating current waveform. And this is very similar to the earlier current waveform which I showed you, which means that this is very rich in input harmonics, current harmonics. In other words, stating it in a different manner, the amount of the conductor size, the transformer size, and then all the power delivery equipment which has to support this kind of a current is much bigger than what actually we need from a shaft power point of view. So we have to deal with this reality to reduce the size of the system, to improve the efficiency of the system. We have to somehow improve this current waveform. Some popular techniques used in the industry basically are active techniques, active front-end rectifiers. We'll discuss the active front-end topology and how it influences the system cost as well as its performance. Then we have the shunt active PWM rectifier, which is a variation of the PWM rectifier. Yeah? And then we have the non-regenerative active front-end rectifiers. And I'll also discuss the active and passive 12-pulse schemes. This is a typical PWM rectifier scheme. It is an active front end here. And as you can see that instead of using a diode front end, we are having 6 more switches. You see? Which means that this is much bigger in size and much more expensive because we have extra switches here. And the output, the waveform here is a PWM waveform. It's like a boost converter. The current flows through this one and returns back here, and it's chopped and it's boosted back up to provide a DC bus voltage here. And the current flowing here is continuous, is made to be continuous. As you can see, the current is very continuous here. But this current has some high frequency ripple. As you can see, there is some amount of ripple here. And in order to reduce the ripple, we have this kind of a capacitor. And most important part of this filter is that this is PWM and this is sinusoidal voltage waveform being supplied from the supply system. We cannot mix the two together without an intervening filter here. That's why we need this kind of a filter. The filter is big and bulky in size, and again you have the switches. So the overall system cost of this equipment is quite significant. However, if the load which we are dealing with is very large in power, like 500 horse or 700 horse or 1000 horse, then it may be logical and it may make some sense to use such type of active front-end scheme to reduce the harmonic imprint on the power system. However, there are some important drawbacks that we have to understand with this kind of a system. The first drawback is that the PWM converter has to be rated to handle full power of the system. So if it is a 500 horsepower or 1000 horsepower system, the PWM rectifier has to be rated for 500 horsepower or 1000 horsepower system. And the input filter has to be also rated to handle 500 horsepower or 1000 horsepower amount of energy in this. So basically the system cost is very high, and the size of the input filter is also very large. Now I would like to bring to attention something which I just mentioned, system cost. When I talk about cost, you can see that there are semiconductor devices here, there is iron and copper here, and there are capacitor film capacitor is being used here. These are system costs, and they are basically commodity costs which are traded on the stock market or on the open market in the whole world. And these are costs which are dictated by human beings. This is not the actual cost which I'm talking about. I'm talking about the environmental cost. The environmental cost is what we should, as engineers and as future environmentalists, we should be aware of it, is what is the system cost? What is the cost on the environment? And if we cannot justify plundering the earth or making or using these resources to reduce or to improve the system efficiency, we have to have, our priorities have to be straight. We have to find out how much energy savings can we afford or can we will result in using this topology, and what are the consequences, how much of resources are we using to create this effect, you see? So there has to be a balance. For a small power system, for small loads, we may not be able to justify use of all these components. But for very large loads, maybe it is possible for us to justify it. But another way of looking at it is to use this intelligently so that it can be used for multiple drives, not for just one drive on our drive-to-drive basis. And that is the topic of the next scheme here, wherein we move the active filter in shunt, and there could be not one drive but multiple drives on this scheme here to result in a much more cost-effective manner of utilizing resources to still improve the system efficiency and the system performance, and from a system point of view. And personally speaking, this is much better from a systems point of view or from a carbon footprint point of view than this scheme wherein this is one-to-one scheme. But the concept is exactly the same type of active filter is being used here, but it is used in shunt. And now you can see that the amount of harmonic correction that which can achieve is much better than the previous scheme. This can be rated to 1/3. The actual power which we need is typically 1/3 of the load, which means that though this is a 90 amp module, it can do harmonic corrections up to 270 amps of nonlinear load can be connected. Whereas if we went to this scheme, a 270 amp load would require a 270 amp filter or PWM front end here. Whereas here only a 90 amp shunt active filter can do the same performance as if it were a 270 amp active front end system. So this is a much more cost effective and much more prudent way of using active topology. The next scheme which I'm going to discuss today is a non-regenerative active front end scheme. In these schemes here, the energy can flow backward also. From the load, it can go back to the system. This one, you cannot have that one because with this nonlinear loads in the form of a diode here, we cannot have energy flow back into the system. Same thing here, energy cannot flow back into the system because of the diode front end. But it is a very cost-effective manner because we do not use multiple switches. We just have 3 bidirectional switches and a 20% or 25% input inductor. But this switch is rated only for 30% of the actual current which is needed. It is in shunt. It is not carrying the bulk power. So this is another cost-effective way of reducing the carbon footprint or improving the system efficiency and reducing the input harmonics. You can see that you can get very good power factor, very low distortion. But again, one of the biggest drawback is that for small sizes, it may not be really worthwhile investigating this kind of a solution. But if the load size is very large, 500 horse, 1000 horse, this may be a good candidate for use to reduce the carbon footprint or to improve the system efficiency. This is the active 12-pulse topology. This is an autotransformer, not an isolation transformer, and it also is very small in size, 1/3 the actual load. And here also we use topology wherein typically autotransformers cannot be used for a 12-pulse scheme because of the fact that the highest voltage actually wins over, and so the currents flowing from L1 will go back into L11 instead of going back into L2 or L3. So in order to facilitate that the currents stay within its own confines here, we have an active switch, and when this pair is on, this pair is off. When this pair is on, that pair is off. So by doing that way, by switching on and off in 50% duty cycle manner, we can force the currents to be concentrated in one section and the other section without having cross current regulation or without having a crosstalk problem. By doing that, we can get very good harmonic performance. Of course, this is a line-to-line voltage and this is a phase voltage, so there's an automatic 30 degrees phase shift. But if you look at the line to neutral voltage, it will be in phase, so the power factor is very, very good. The harmonic distortion is very low, but again, this is one drive to one load application, which may not be very suitable from a carbon footprint point of view, but may be relevant if the size of the drive becomes very large. In fact, we could have a DC bus and we could have multiple drives on this DC bus, and we could have one big or one cost-effective AC to DC active rectifier, and we could have our DC transmission with many loads on this, then it would probably make more sense. The most cost-effective solution, which I feel is the best for most industrial application, is to use a simple autotransformer and phase shift them and have a bunch of drives on one set of windings and a bunch of drives on the other set of windings, and allow natural cancellation of harmonics onto the power system. And we have done many studies like this, and we have seen that depending upon how well these bunch of loads are balanced between this set and that set, you can get very good harmonic performance. And this probably would be the most cost-effective solution to reduce the carbon footprint in a given power system, because you can get very good natural cancellation of the harmonics by using a very small autotransformer, which is 30% of the total load. If the total load is 1,000 horsepower, we would need only a 300 or a 350 horsepower autotransformer. And we could bifurcate, or we could divide the loads and spread them out into two different sets. You could have the first floor to the third floor or the fifth floor on one set of windings, and from the sixth floor to the 10th floor you could have the other set of windings. And natural cancellation would give you the best performance, and this would be the best solution from a carbon footprint point of view and from an system efficiency point of view. So in conclusion, what I have discussed today is harmonic distortion is important to reduce harmonic distortion from efficiency as well as from power factor or VAR point of view. It's important that we should consider this. And the intention is not to make the current look pretty. The intention is basically to improve system efficiency. And that should be the main motivating factor, and to reduce the VARs necessary in the system. While discussing cost, again, we should refrain from using commercial costs, because these commercial costs can keep changing depending upon the stock market and depending upon how one bets against copper and against iron. But the actual cost to the environment is constant. So when we talk about cost, we should really concentrate on the cost to the environment and not commercial cost. Finally, as power quality considerations evolve, Yaskawa has a continued opportunity and responsibility to recommend equipment and countermeasures which both allow the customer to enjoy the best value from a cost point of view and the highest system efficiency. Thank you very much.